Well, that was a small portion of what we talked about, right? But what air is doing what exactly? Yeah, but the null hypothesis is an hypothesis we make when we do what? Like, what's the topic called? It's an example of inferential statistics. That's too broad. We're doing hypothesis testing, right? And part of that's the null hypothesis. But remember, your real hypothesis is typically your alternative hypothesis. Your alternative hypothesis is what you really believe, right? So we'll finish the two sections, and I'll do some more examples of of hypothesis testing, right, in class next week, and then we will do our very last chapter, which will be short, right? It's going to be about regression. So we'll finally have regression, right? We've always been talking about one thing, one measurement, like what's the distribution of mean height, right? Or people's heights or stuff. Now we would say, well, what's the relationship between heights of people and maybe weights of people, right? Something like that. Okay, so in this class, you will be doing hypothesis testing, right? Every hypothesis test, and this is why I focus mostly on this, it's going to be either, there's a section in about standard deviation, but like that's obviously the thing that you'd be the least interested in, right? So everything is either going to be a claim about a proportion, right? So here's a claim about a proportion. More than 10%, more than 10% of men are 6 feet tall or more, right? Then you might test a claim about a mean, right? The mean height of men is more than 5'10", right? Something like these are claims, right? So a proportion is a yes or no question that each member of the population would have an answer for, right? So some percentage would be yes, some percentage would be no. So here are our test claims, right? We want to use test claims using the techniques and stuff that we discussed last week, right? But we're going to do it today, right? We're going to use this terminology, and then we will make guesses and assumptions and kind of figure out what we're doing here, right? Okay, so here are assumptions about a claim, right? And some of this terminology isn't very new. So to be able to use the methods, right? We all use this normal distribution stuff here, right? So we're assuming it's normally distributed, which means you need to know that one, this is always true, right? So if I want to figure out what portion of men, right, I have a hypothesis about the heights of men in the United States, right? People should be randomly placed in my sample, right? That's the number one thing, right? That's always the case. These other cases saying it should be a binomial distribution. So that means that the placement of each person into the trial should be independent, right? Now, this is not actually true because, right, if I put Bobby into my sample, right, the probability that Brian would be selected and the next one goes up a tiny bit, right, because there are fewer men. But we can assume it's binomial because the population that we are going to be doing a hypothesis about is usually so large that this would be a tiny change, right? It's goes from 1 in a million to 1 in 999,999, right? It's like it's a binomial distribution, right? If it wasn't, we could just collect, if putting one person into the sample affected the probability of someone else being, if that was significant, we probably have access to the whole population, right? We wouldn't need to do all of this. And everybody refers to the, killing me guys, the sample size, right? And it even says that there. So NP is n times the probability that you're testing, right? So what this basically means is that you should have 5 people in each group, right, in your sample. So if I'm testing, if I'm interested in the proportion of men that are over 5 feet tall, my sample should be big enough that I would have at least 5 men over, well, not 5 foot tall, let's say 5'10", right? There should be 5 men in the sample that are over 5'10" and 5 that are under it, right? So this is the stuff to even be able to use the testing. Notice I'm not teaching you how to do the test, right? And here's the notation that you use. n's the sample size. Your sample proportion, sometimes that's given, sometimes it needs to be calculated, right? But it's very easy to find the sample proportion. If there are 30 people who are over 5'10", and there are 40 people in the sample proportion would be 75%. A lot of time that's not given directly, right? The population proportion is what you're making a hypothesis about, and Q would be 1 minus that. And you calculate this test statistic. Questions? Okay, so I'm going to go through the steps, right? I'm going to try to do this slow enough that you can write it down. But again, remember, this is all on the internet, right? So Canvas, in the modules, each module has a title, right? And then each module is for each chapter, and then each presentation is named by the section, right? So this is, please tell me that the rest of y'all, oh, why is this on there? Uh-oh. Okay. What do I want to, just give me 1 second here. Oh, you know what? I'll do that in a little bit. We'll take our break early. Okay. So I can give you some time to write this. So the p-value method of testing hypotheses, right? So how do I do that? Well, the p-valid, this p right here refers to, just be careful, right? This p, the uppercase p, we're talking about our probability, right? I'm gonna write cap. Lowercase p, we're talking about proportion. You'll see the difference when we do this, right? So first step is to identify the original claim. You don't need to do the opposite. That I'm not really a big fan of. And you put the original claim in symbolic form. So that means like with variables and stuff, right? So if my claim is, all right, Bobby, what percentage of men do you think are over 5'10"? So you think 30 or more percent, right? Let's just say that. So that would be P is greater than 30. That's what I'm looking for, right? Then you want to identify the null and the alternative hypothesis, right? Almost always, so remember, your null hypothesis always has what type of sign in it, everybody? That chi is not a sign. And that was way different. Null hypothesis is always a claim in the form of something. Let you guys find it. This is important. We spend a lot of time talking about it. Intentive. Are we looking it up? What is, I don't remember anything. A null hypothesis, guys, is always a claim that a parameter equals something. Does everyone remember this? I mentioned this many times on Wednesday, right? The null hypothesis is always a claim, right? And then the alternative hypothesis, which sometimes you see as H1, sometimes you see as HA, is typically what you actually believe, right? It's typically going to be the same as the original claim, right? It's always going to involve not equal to, less than, or greater than. You're going to identify the significance level, right? That's going to be given to you, okay? You calculate the test statistic. In the case of the proportions, right, we have a formula for that. You're going to sketch the test statistic, and either using a calculator, and you're going to identify the p-value, right, which you'll be able to do by sketching it out using a normal distribution. Then you reject the null hypothesis if the p-value is less than or equal to, and you fail to reject if the p-value is greater than the significance value. Oh, perfect. Okay. I do need to grab something. Power cord. So, this is a bit of notes to write down, right? So, write this down, right? And then we will go over this example in just a bit, okay? I left my power cord and it's going to run out of power. So we're going to take a minutes break right now. We have roughly these steps written down. Hopefully we can find them later, right? Okay. So let's try to look at this, right? Well, 2010, the year I graduated college. All right. So has anyone here ever taken a drug test for a job? Yeah, okay. So I haven't for a long time. They don't do it here, so you don't. Any of your professors could be on drugs. You don't know. All right. I mean, maybe that's better. They'll be more likely to be put up with you if they are. I don't know. I don't know. I'm kidding, guys. I'm kidding. It's not. Don't report me, please. Okay. All right. What happened to the? That's weird. Okay. Why did it dis? That was weird. Okay. Ah. All right. That's the right slide. Sorry. So in that year, right, of the people who applied, right, 5.8% failed the drug test, and I'm sure most of those probably thought that they had some genius method to pass it that didn't work, right? Okay. So we now got at the 0.1 significance level, so that means that they only want to. So just to remind you, significance level, right? Significance level is that we only want to reject our null hypothesis, right? But if we're 99% confident that it's wrong, right? We want to see, okay, like where our value, our test statistic is so extreme that there's only a 1% chance that it would be that extreme or more, right? And then we'll get into that a little bit, right? Okay, suppose you say, right, now people are brighter, economy is different than it was there, right? So we're testing the claim that the failure rate, right, you believe the failure rate that now fewer percentage of people, you think, right, let's just imagine this, right? Gina goes and she thinks that seems way too high to me, that percent of people fail it, right? People who are on drugs, they just don't apply for these jobs, right? I don't know, whatever you might think. So that's your claim, right? And then Regina, she gets a random sample of 15, 20, right? That's the size, right? And it results in a certain number of failures, right? So we're going to go through this whole thing and we're going to test the claim and then make a conclusion, right? All right, and we're going to use the p-value method. There's also the critical value method, which I will teach in a bit here. All right, so let's just go through each of the steps that were on my previous slide, right? And then we should have the answer to what's up. Just a second, I think. Yeah, I must have done things in different. Oh, okay. I remember about a year ago, I changed the order that I taught the two methods because I thought one was more intuitive and I couldn't figure out what was going on with my notes there. They were in the wrong order. Okay, so nonetheless, step one was to, okay, so the original claim is what the tester actually thinks, right? So first let's say that in words and then let's try to figure out how to write that symbolically. So what does the person think? That was in 2010. The symbolic claim is, I'm going to say, always has an inequality in it, typically. I'm going to say, yes, always. P is not great. So where are you getting 58 from? The number of failures? So P stands for, no, not this one. What is this title? What is this section titled? Testing claims about a proportion. So P is a proportion, so it should be a number between 0 and 1, right? So that doesn't make sense. We're not there yet, right? We need to identify what is the person who is doing this, who collected the sample, what do they think? It's in the second sentence. Lower. So failure rate, that really means proportion of people who fail the drug test, right? So let's look at this. The failure rate is lower, right? The failure rate is lower. So lower means less than. Lower than what? 5.8. I'm going to write that as a proportion because you want to be careful with our formula. So that's 0.058. You could also write this in words, right? The rest of you who had trouble seeing this, are we able to see this now, that is what is actually believed by the person doing this, right? That's roughly, they says test the claim, right? It's kind of in that, but that's what you think. You can write in words that, I don't know, you don't have to write anything in words as far as I'm concerned, but if you want to think about this, right, you're saying, right, I'm just trying to drug test now. I can't rate everything. So basically, I think fewer people fail drug tests now than did back in 10, right? And back then, that was 5.8, right? So basically, roughly thinking, I think the proportion of people who fail drug tests is less than 5.8%, right? All right, so let's get moving then. This is going to take a while. Jesus. All right, so step 2, what's the second thing you need to do? Null hypothesis. No one could find it, but one over here. Null hypothesis, everybody always has what sort of sign in it? Equal sign, all right? So your null hypothesis is, so we're making a claim about what? The proportion of people who use drugs. So the null hypothesis is going to involve what letter? P. The null hypothesis is going to be P is what? V is equal to, 0. Okay, right? So, right, like P, like the null hypothesis is kind of saying, I'm skeptical of what you think, right? I'm going to default to common wisdom and accepted value, right? So typically your null hypothesis is accepting, right, like what was generally held to be true for many years, right? That's not exactly it, but like that's roughly the idea, right? But another thing you can think about is the word null means no, right? So the null hypothesis is an assumption that there has been no change, right? Or that there was no mistake in the original idea, right? So the null hypothesis is, in this case, is same number of folks failed drug tests as they did back in the day, right? Now, your alternative hypothesis is typically what you actually believe. And it's always going to involve an inequality sign, so greater than, less than, or not equal to. In this case, it's going to be, now when you look at this, right, from the null hypothesis, you also have to tell me what type of test, right? And we're looking at tail, left tail, right tail, or two-tailed. And you can get that by just looking at the type of inequality. So it is going to be a left-tailed, right? Left-tailed because it is less than. Step 3, not let me write anywhere close over there. Okay. Step 3 is to do what? This is actually, in my opinion, the easiest step. Not, it's just, yes. So identify the significance level, which is alpha. The significance level here is literally stated 0.01, right? Okay, so this is the start. Now 4 is to do what? The test statistic, right? So we need to calculate the test statistic. And the test statistic when you do a proportion is always Z, okay? Yes, and then you need to know the formula, right? And then we need to figure out how to put the numbers into the formula. All right, so the formula is P hat, what's the rest of it? Minus P divided by square root of PQ divided by N, right? We just gave that. So, say that again? Yes, absolutely. Just like, in algebra, 3x means 3 times whatever x is. Yeah, absolutely. Okay, now, some of these we have in the very straight, let's try to identify some of these. P, everybody, is what value? I'm just giving me a number. What is P equal to? Point? Yes, but yeah, you have to write it as a, right, okay. Right? Now, everybody, N is equal to 1520. That's much of what's in our formula. Now, Q, where do we get Q from? 1 minus P, so that is 0.942. Here's the tricky question. What is P hat? So first, let's remember, what does P hat stand for? Proportion of the sample, right? In this case, our proportion is 5. So of our population, we think it's 5.8, right? And that 5.8 is the percentage of people we think who failed drug tests. Now, I'm not given, I'll tell you, you cannot find p hat. It's not like the other thing, I just pull it out, right? Like it's a number, I pulled it out. I cannot do that, but it can easily be calculated from here. How? Say that again. X over n, right? We're going to use X over n because X is the number of failures, right? And then is the number of the sample size, right? So that would tell you what percentage of the sample fails the drug test. Is everyone following what I'm saying here? Notice, right? If I asked you, see, this is just that there's steps, right? If I asked you what percentage of people fail the drug test, if you have 58 failures and 15, 20 applicants, right? You could easily tell me that, right? But sometimes it doesn't occur for you to do that here. And if you throw that in your calculator, you will get, and I wrote it down somewhere, approximately 0.38. Okay. So that's your p hat, and then you can just plug all that stuff into the formula. Now let me just point out something, right? This is kind of makes sense why this person has this hypothesis, right? You're told, hey, 5.8% of people who take employment drug tests, they fail it, right? But you yourself, you took I don't know how you did this, right? Simple random samples are very hard to take, but just imagine you did, right? You took a sample and you find only 3.8% of them failed the drug test, right? And this isn't a half-ass sample, right? You really, you have over 1,500 people in this sample, right? So that's a significant size. So anyone who sees this, right, you would say, I think it's lower because this is lower, right? But is it that much lower? Is it low enough, right, that it's unlikely to have occurred by random chance, right? Because we don't know yet, right? That's what we're calculating, right? You think that it's not, you think that it's too low to have occurred by random chance, right? Is that what you're saying? You might, okay, I'm not sure, right? Because it doesn't seem that big of a difference, but it is when we're low, not like a small change in 3 to 4%. That's a decrease by 25%, right? So like it seems significant. It might not be, right? So what we're saying is that 5.8 is our conventional wisdom, right? Since our significance level is 0.1%, we only want to basically reject our null hypothesis if the chance that this would happen by random chance is less than 1%, right? If this could randomly happen by chance by 10%, oh, that probably didn't happen, right? But like things that happen with 10% chance of happening happen all the time, right? So we said, let's do 1%. Okay, and the only way we can do that is to calculate our test statistic and then use our p-value method. Okay, so let's do that, right? So this is nice. You just use a formula. Notice this is just difference, and this bottom thing is standard deviation. Now, one thing I forgot to do is check our requirements. The big requirements is simple random, which yes, right? And the other simple is NP and NQ. Both have to be more than 5, right? So in the context of this, that means there have to be 5 people who failed the drug test and at least 5 people who did not. We passed that with flying colors, right, guys? Okay, so when you type this in your calculator and you're careful, you get Z is negative 0.334. This is a Z-score, right? Okay, so what is the next step that we do? We just did step 4. Now we're doing step 5, which is to, okay. So this thing has a mind of its own right now. What the hell is it doing? Something's wrong with my keyboard. That is what is up. Oh boy. All right. So we want to sketch the curve, right, depending on this. So remember from the previous step, we got Z to be negative 0.3. And what type of test is this? Or sorry, the tail part of the test, y'all. It's a left tip, right? So that means you sketch to the left. So let's draw this out. So here's our center, right? Now our Z-score is located to the left or to the right of the center? And are we doing a left or right-tailed test? So do I shade to the left or to the right of the line? Left, the same way you do the tail, right? Now the rest of that step says, I want to find out the probability that I am to the left of that value, right? This is why it's called the p-value method. Okay, let's find that p-value. Just remind yourselves how to do that. So get out your Z table and find the p-value. Just hang on a second. Let other people do it, all right? While y'all are doing that, was anybody not here on Wednesday when I passed back these celebrations? Okay. You'll have to give me that back at the end of the period, y'all who are looking at it. Here's an answer key to compare it to. If you find any mistakes, just make sure the answer key to compare it to, okay? Okay, Mars, tell me what you got. 0.00, so it's 3 zeros, right? I got 4.3, but not a big difference, right? So let's just take a look at the table. Yeah, I got it wrong. It could be me, it doesn't matter. So we go to, actually, I'm just going to say that you're right. Okay. I don't have it on this part of the table, right? It's not further on the table, right? So we just look for, right, that z-score, right? And since we're doing area to the left and the table already gives you area to the left, we don't really need to use the table any differently, all right? Also, I want to point out here just before that alpha is 0.01. So this area right here, aka the probability, is 0.00043, right? So what does that mean? Let me explain what that means. So what we just calculated, right, is, right, let's assume, right, so if, right, everything is the null hypothesis, right, you're using the null hypothesis as your assumption. So our assumption is the drug use rate of job applicants, or the drug test failure rate, maybe the test doesn't, the failure rate is the same, right, as it was back in 10, right? And then we calculated, okay, based on that, we found this z-score, right? So this z-score says how far is what the test rate, failure rate we measured from the test rate that we think is the actual rate, right? We found that it was 3 1/3 standard deviation lower, right? By looking at the table, this area right here, this is the probability that we would get a test rate, right? Our test rate was lower than what we expected. Would everyone agree with that? It was 3.8 instead of what was it supposed to be, 5.8, right? The probability that would happen, that we would get a test failure rate of 3.8 or lower, the probability that would happen by chance, if the failure rate was actually 5.8, is 0.00043, right? That's pretty unlikely. So that implies to me that our original assumption is false, right? So let's take a look at this, right? So what you do is you notice, so this is how you decide to reject. So step 6, what did step 6 say? Okay, so what did we say? How did we compare our p-value to the significance level here, everybody? It's definitely less than, right? It is a lot less than, right? So what this is saying is, we were skeptical in the first place. We said, I only want to reject my null hypothesis if my value has less than a 1% chance happening, less than a 1% chance of happening by chance, right? So we said, hey, assuming the null hypothesis, assuming no change, we would only find a sample like this 0.043% of the time. That's pretty unlikely, right? So that implies to us that we should reject our null hypothesis, right? So this means this. So then we want to, so then 7 is to, yes, go ahead. Yes. Absolutely. That's how you do it. You compare your P, right? So our alpha is our threshold, right? If something's, we said we only want to do it if we have overwhelming evidence in this case. And we defined overwhelming as less than a 1% chance of happening by chance. Our result has a 0.000, or let's see, no, move to death, 0.043% happening by chance. That's pretty, not only did we reject it, I'm not at all uncertain that we're making the right, this is very unlikely to occur by chance, right? So we're rejecting it because this is something, if you just think about it, right? A small p-value means it is unlikely to happen by chance, which means your original assumption is probably wrong, which means you want to reject your null hypothesis. Because remember, right, the test statistic, z, is calculated assuming that p is what we think it is. Or not what we think it is, what people used to think it was. So let's state this in so step 7 is to state this in everyday terms. So so when you reject, you always want to say there's sufficient evidence. So when you reject, you're always supporting your alternative hypothesis, which is typically what the experimenter actually thinks. So the null hypothesis in this, sorry, let me start over again. When you reject the null hypothesis, you support the alternative hypothesis. And the alternative hypothesis in this case was that, yeah, P is less than, now let me state that in words. So this claim, right? This is saying there actually is, in other words, there's sufficient evidence to claim. So I'm going to just write AKA instead of a sentence, AKA. All right, are we following here, right? So basically, right, the chance you would get something that has that low of a failure rate, a sample that's, if you did this in 2010, back when we know that that was the value, right, the 5.8%, the probability that you get 1,520 people, right, randomly selected, and 3.8% or less of them fail the drug test, right, that it's that low, the probability of that happening back then was 0.043%. Pretty low. So since the probability of that happening back then is so low, and you know it did happen right now, I think something's different. And that something different is the alternative hypothesis. All right? We following, folk? Okay. So let me do another example by using the other method. This method is very similar. It's just the ending part that is. So please don't rush to write all this down, right? So this is the critical value or traditional method. It's called traditional because it's more difficult, because this was easier to do back before they had with computers, right? With the Z tables. You could use less information to do this, but I find it less intuitive. So don't write everything down here. Let's identify, because most of these are the same. So step 1. Is that the same as it was in the p-value method? Everybody, is that the same? We are deciding whether this procedure, right, is a new way of doing hypothesis testing. But it's very similar, right? So instead of having you write all these steps down, we're going to compare it to the other one and see what's different. Yeah, that'll make it easier, right? So this first step, is it the same? Yes, okay. Second step, that's the same. What about the third? And the fourth? It's the same. So you don't need to write that down. Let's see, what about the fifth step? It's not quite the same. So before it said identify the p-values, now it's identify the critical value. And you identify, so this is different, right? So this is different, and then really, this next one is different-ish, but it's basically the same, right? And the last one, of course, is the same. So here's the difference in this method than that method. So in that method, we found our test statistic and found the probability corresponding to that, right? And then we compared that probability to our significance level. In this case, we have a significance level. We find a critical value corresponding to the test statistic. No, sorry, we find a critical value corresponding to the significance level, and then we compare that to the test statistic, right? So each Z has a probability, right? It's basically, are we comparing the Z's in this example before we compared P's, okay? So that's the difference. So let's go through this, and you'll see it's fairly similar, and then you can let me know which method you prefer. All right. Has anyone heard of Lipitor? They used to advertise it on TV a lot, which is weird, but it's a heart drug, right? It's a drug that people who might have issues with cholesterol or whatever take, right? So we're seeing, right, and they're saying, hey, maybe this drug causes people to get the flu, or not the flu, but flu-like symptoms, right? The flu is a disease, so that wouldn't be possible. But you know, if you just randomly get it, it's funny, but you know, 1.9% of any patients, they just say I'm experiencing flu-like symptoms, right? So we want to see, is this group, right, have higher flu-like symptoms than the regular population, right? And do they and if yes, is it a statistically significant difference? Right? That's what we're always trying to find out. We're trying to find out basically, does this thing cause flu-like symptoms? Right? Like if it's more than 1.9, it causes it, right? That's the difference. But we have to see if that is significant. Okay, so let's start out with what is the original claim. So let's think about it. What do we want to know? We want to know if this drug, if it does what? Okay, so that means that the flu-like symptoms should be bigger than what they are in just a random group of people that aren't taking this drug or anything. Okay, so this is again a claim about a proportion, right? In this case, the proportion is greater than, and greater than what? Yes. So that is our original claim, right? So step 2 is to, yes, okay. Remember, David, the null hypothesis always involves what sort of sign? I'll give you a hint. I'll show you the previous one. No, it's all right. Everybody, the null hypothesis always involves, everybody say, what sign? Equal sign, okay? So the null hypothesis in this case is that 0.019, and the alternative hypothesis is that, okay, Bobby, step 3 is to identify the, oh wait, I didn't finish step 2. In step 2, I have to write these in. I have to say the type of test as far as, this is right tail because greater than. What do we do in that third, Bobby? And in this case, it is, yeah, so same as before, 0.01 the last time, right? Okay. Step 4 is to calculate the test statistic. And the test statistic for proportions is always represented by what letter? Yes. Now, that won't always be the case. We will have T when we get into the mean stuff. Okay. And the formula for Z when you're doing proportions is P hat, P. That's right. Okay, perfect. Good job. So let's just throw that in. Now, in this case, Q is going to be 981, right? 0.981. 1 minus P, right? Other thing is, do we have enough, right? So remember, are there at least 5 people in this sample that experience flu-like symptoms and 5 that don't? Yeah, because we're looking at about roughly 2% of 800 people, right? That's more than 5. And then N in this case, everybody is. Now, is P hat directly given in the story there? Like, is the number quoted in this paragraph? Just remember, what does P hat represent, folks? It represents the sample proportion, right? We're not told a sample proportion, but we have enough information to calculate it. So what is in the sample, right? We want to know what portion of the sample experienced flu symptoms, right? Well, we don't know the percentage, but we do know the number of people who experience flu symptoms, and we know out of how many, right? You throw that into your calculator, and you're going to get, yeah. Be very careful when you type this stuff in your calculator with the parentheses and stuff. I will show you how to do the whole thing with the calculator on Wednesday, all right? So see this, right? It's not always our intuition is wrong, right? So not to pick on you, Mars, you previously thought that the change in percentage was something that could have easily happened by chance, right? And were you right? No, it's hard to get intuition of this, right? So let's see here though. So this represents 2.2%, right? So 2.2% of the sample has flu-like symptoms. And so we want to see, is this sample significantly different than the population? Right? And the population we know is 1.9, right? So this one we now know that, do we have anyone have any intuition about whether this is different enough? Hard to say, right? But it is larger, right? But the question is, it went up by about 0.03%, right? The question is that enough of a change to be considered significant? Enough of a change to not have happened, that it's unlikely to have happened by chance, right? Is everyone following what I'm saying, right? It went up, but did it go up enough that it was unlikely to happen by chance? That's what you're always doing in a hypothesis test. So when you calculate this, you're going to get a z of 0.64. That's equal to z. Okay, so this is the step that is very different, guys. So who can read to me step 5? Our new step 5 for the critical value method. Yeah, right? So some of you may have heard that. We want to sketch the curve and identify the critical values in the critical region, right? The critical values in critical region is not the test statistic, right? We want to find out if the test statistic is in that region, right? But we'll depend on it. All right. So everybody, was this a left or a right-tailed test? Right-tailed, right? Okay. And what was our significance level? All right, so let me show you what this means, right? So this is definitely not to scale, right? Because it's supposed to be 1% of the area, right? You wouldn't be able to see it. So I find this one less intuitive than the other method, right? The p-value method. So that's why I wanted to do this one second. So this is our significance level, right? Again, we only want to reject, right? We're saying that a drug that is made by a very profitable pharmaceutical company, maybe some of you will work in the marketing department of, and you'll be the ones making those ads, asking if you have mesothelioma or whatever the hell's going on there, right? We don't want to say that it causes a side effect unless we're sure of it, right? And we say we want to be 99% sure, right? So we want to know that our sample has a less than 1% chance of happening by chance. So we want to see, is our sample in this critical region, right? And this is the z distribution, right? So we want to find out, what is this critical value that cuts off the 1% from the 99%, right? Does everyone follow what I'm saying here? Once we know what z-score this is, we can compare our z-score of our sample, right, and see if it's in the critical region or outside of it, okay? So let's flip to our table again. Now, we want to find, this is a little bit different, right? So our z-table gives us area to the what of the z-score? To the left. But our value is to the right. So 0.1% is the area to the right. What's the area to the left? 0.99, right? And then remember, the numbers inside the table, inside is area, right? We have an area, but we need to find the corresponding z-score, right? So I'm going to look for 0.99. Notice it's going to be somewhere around Yeah, we want to find, so notice here it's just under 0.99, and then here it goes over. So I'm going to just say it's in between those. So I'm going to say that my critical value is 2.325. So that's our critical value. Now, where is our test? What's our test statistic? We calculated it before, moments ago. Okay. Yep, it is. Definitely not to scale. So it's some to the right, 0.646. All right, this is our test statistic. It's a 5, doesn't really like an S there. Now, our test statistic, so step 6 is to identify whether what? True, but yeah, let's talk about how we do that, or whether we can reject it or fail to. You never know if it's true, right? Yeah. Right, yeah. But you can see the null hypothesis is, right, it's hard to get a specific, because it's saying it's a specific value, right? So we just default to it if there's not overwhelming evidence. So let's think about this. Our test, so we said we only want to reject if it's less than 1% chance of happening by chance, right? And we said the critical value that cuts off like the top 1%, right, is 0.2325. Is our test statistic in the critical region? Our test statistic is not in the critical region, so does that mean we reject or fail to reject? Absolutely. We fail to reject because our test statistic, right, we want to, right, to think about it, to overcome accepted wisdom, we want overwhelming evidence, right? That means we want something that is extreme. It's more than in this case. It could be like if it was a left tail test, it'd be less than, but it would be more negative, right? So in this case, we would say, right, so we would look, instead of comparing the probability, right, we know that our probability, but we're doing the same thing. I don't have my probability, but I know my probability is going to be greater than because that area is greater than, right? But we just use the critical value instead. So my TS, is that okay for test statistic? We got that, right? Test statistic is not in CR, which means critical region, right? So last step is always to rewrite this in everyday language, right? So another thing, right, as just to point out, because I know Regina just forgot, when we say fail to reject, we don't know that the null hypothesis is exactly true, right? But what happened isn't unlikely enough to say that it's false, right? So what we would just say is there is not, and say sufficient. I'm going to just write enough because it's shorter. So in this case, we're saying there's not enough evidence to say that our sample is any more fluey than any other random group of people who are not on Lipitor, right? So we would say there's not enough evidence to support the claim. And the claim, roughly speaking, is that Lipitor causes. Now, maybe it's true that that extra 0.3%, it really was caused by the Lipitor, right? So small effects are very hard to detect statistically, right? Perhaps Lipitor does something to a tiny portion of the population that makes them have the flu, or not the flu symptoms, right? But based on our sample size and the size of our based on the size of the effect and the size of our sample, we don't have enough evidence to say it wasn't caused by chance. So if you really thought, let's say you still think, I think that Lipitor causes a very minute but real effect in flu symptoms, you would need a much bigger sample, right? So that you could pull that. Which method do we like more, the p-value method or the critical value? Who liked the original value method more? I think, does anyone else like the p-value method, like what we did for the first example, more than this one? Yeah, I think so. That's why I did it first, because it's more intuitive. It is, yeah. Although the reason why this one is notice that, yeah, we had to kind of use the table backwards, but you only had to do that for the significance level. And usually we have like 3 or 4 significance levels. So you could have a table with just 3 or 4 values, right? That's the advantage of the other one, right? You could have that. And you could even just know you can even just write down the critical values for those most common significance levels. So that's the advantage. And we'll turn out for some claims about a mean, which we'll try to start just because I want to get as far as we can before we get to I want us to finish stuff. I could either be a day and a half. I want to have as much time for you guys to work on the take-home celebration as possible. So that's going as far as we can every day. Even though we have 15 minutes. So before we tested claims about a proportion, right? What proportion of these have flues, right? Now we are going to test claims about means, right? And then the lesson that I'm going to do after this is going to have those sort of claims like kind of mixed together, right? And then that helps you distinguish what's going on. Yes, Rena.